Okay, ladies and gentlemen, good morning to you guys. This is Math 261. Okay. What were we working on? Do you guys remember? Related rates. Okay, and we looked at first example, particle moving along a curve, and you know, you can spend weeks on this topic. It's a great topic. You can spend a lot of time, but you know, we can't really do that. Let me give you guys another example here, more examples. Here's a classic question, the oil spill question. Bless you. Here's a classic question. What does it say? I don't know. Oil spills in a circular pattern. Okay. With the radius increasing at a rate of 1 meter per second, okay? Question's going to be how fast is the area increasing? When the spill has a radius of 30 meters. Okay? So here's a very classic oil spill question. So I think the key idea here is this. Circular pattern, what do you guys think that means? Good job, it's a circle. So you might go, okay, I'm talking about a circle here. You got the radius of a circle, is that true? And then what do they say? The radius is increasing at a rate. So let's write that down. Your radius is increasing at a rate of what? What does that portion in red actually mean if they say the radius is increasing at a rate of 1 meter per second? What do you guys think that means? First of all, the key word is what? Rate. So, and then what letter represents the radius? Good. So what they're saying is the following, right? That dr d what? T is a positive 1. And yes, that's in meters per second. You guys okay with that? So I want you guys to understand this part. dr dt is 1. So dr dt equals 1. How fast is the area increasing when the spill has a radius of 30? So let me do this too. What do they mean by how fast your area is increasing? Because the circle is getting bigger, bigger, and bigger. Is that right? So if a circle is getting bigger, bigger, and bigger, so is the area. So I want to say to you guys, what do you think a good start would be? What's the area of a circle? What's the related rates equation? dA dt. Differentiate both sides with respect to t. And then what happens over here? Chain rule. What do you guys get here? 2r times dr what? dt. So what you see now, this is called the related rates equation. dA dt will be now 2 pi r dr dt. Related rates. Okay, you guys okay with that? 2 pi r dr dt. So what should happen now, when you go back and you read this and you go, oh, how fast is the area increasing? How fast, again, is a rate? What do you think they're asking for? They're asking dA what? In green, I'm going to say this is what they're asking for. They're asking for dA dt. Okay, they want to know, what is dA dt? We don't know dA dt. We want to find out what that is, okay? But they did give us dRdt. What was dRdt? Mm-hmm. So we know this portion here is what? 1. Is that right? And what else do we know? We know the radius. How do we know the radius? What do they say? The radius is 30. It's 30 meters, okay? So r is 30, so that means this number down here is what? This is 30. So, ladies and gentlemen, dA dt becomes 2 pi times 30 times 1, right? Which will be, what does that become?
60 pi.
That's 60 pi meters per second, right? And that's a symbolic answer, bless you. But ladies and gentlemen, that's kind of another kind of classic question here. Okay? That we're working on. Yeah. It's a very good question. You can't use the circumference because you say, why not? But you see that question in green? It's how fast is the area? If they said how fast is the distance around, which is circumference, then you would use the circumference. So because the question is in terms of what? Area. You got to use the area formula. Okay, you guys okay with that? It's kind of a classic kind of question. Some geometry questions, you know. You know, and so, something like, I mean, I think that you got another one. Anyway, let's go to, so I'm going to go to some of my all-time kind of favorites so you guys know. Here's another particle question. It's going to be different than this one. Yeah. It's a different particle question. I like some of those particle questions, you know. And geometry. So a particle moves along a curve. So I'm going to say, okay, a particle moves along a curve, okay, where y equals, and let me kind of draw that a little better if I can. Y equals x squared plus x. Did we do this one? I don't think so. And as it reaches the point 2, 6, the y coordinate is increasing at a rate of 3 centimeters per what? Second. How fast is the x coordinate changing at that instant? Excuse me. Okay. So here's the idea, right? I'm not going to draw the curve. But here's your curve. And I guess that's a parabola of some sort, right? So I'm just going to draw, I'm going to kind of draw just a, oh, what is the idea? 2, 6, x is 2, y is 6, okay? So I'm just going to draw an imaginary curve. That's not the curve. And here's location 2. It's not to scale. Here's 6. Okay, it's not really the curve. I want to emphasize that. You go, Mr. Judge, your graph isn't correct. I know, it's a parabola. But a particle evidently is traveling along this what? Curve. And then it reaches that point. Okay, you guys okay with that? 2, 6. And so they're saying a particle moves along a curve as it reaches the point 2, 6. The y-coordinate, okay, what's going on with the y-coordinate? Let's close that door if we can, before I get scared. The y-coordinate is what? Increasing at a rate of 3 centimeters. What does that mean, ladies and gentlemen? Yep. And I want to say something, too, about that. That's going to be our what? dy dt is a positive 3, and it's centimeters per second. Okay? Because they can even say decreasing, and that's going to be negative. So I want you guys to note this here, okay? Put that in your note. What if they say decreasing at a rate of negative 3 centimeters per what? Second. If they said that, they didn't, dy dt would be what? Negative. I'm just going to put this in our what? In our notes, because decreasing is a negative value, okay? You guys okay with that? Just want to make sure, because you never know. Okay. Okay. Yes. No, it has to be negative. I'll check the notes. If you say decreasing, it's negative. Okay, good job. If they say decrease, okay, good job. If they said decreasing at a number and it's positive, it's negative though. The word increasing and decreasing, okay, if it's going to be, if they ever use the phrase decreasing, put the negative number. They may not put the number. It's kind of like speed. Yeah, exactly. Exactly. It's kind of like speed. You know, speed is always positive. Negative velocity, positive velocity. But yes, if they put this, let me be clear. If they say decreasing at a rate this, now it's going to make some sense. If they say decreasing at a rate of 3 meters per second, there you guys go. It's negative 3. You guys okay with that? Good job. I understand what you're saying. All right, you guys okay with that? Decreasing is a negative value. They may write it down positive, but they expect you to know dy dt is negative. Anyway, just to kind of say that. And then say, how fast is the x-coordinate changing at that instant? So what they want to know is, they want to know what is what? They want to know dx dt. So you got y equals x squared plus x. Okay, so we got to get, since y equals, we get dy dt is d dt x squared plus x. And so dy dt becomes d dt of x squared plus dx dt, just by definition, using operator notation. Okay, you guys see this portion here? What do you guys think you do with that? What is going to happen here? Chain what? Rule. 2x times what? dx dt. So altogether, dy dt will be 2x times dx dt plus what? Yeah, and what you can do on the right side, factor out your dx dt. And really, ladies and gentlemen, this is your related rates equation. So you can use this equation here now. You say, what do you mean, how do I use it? Well, what did they say? dy dt in orange here is what? 3. So you go, okay, this number here is what? 3. And then you say, well, what is the x coordinate here? Here's x, here's y. So x is going to be 2. And you say, well, how do I use the y coordinate? And I'll say you don't, because it's not even there. They want to know what dx dt is. Okay, what is that dx dt? So it's okay for you to use that information now. So this is 3 equals 5. Is that right? Times dx dt. So what would dx dt actually be? 3/5, which would be actually 0.6. Was it centimeters per second? Centimeters per second, I guess. Is that easy peasy lemon squeezy, ladies and gentlemen? That's an easy one. Yeah. Yes, yes. So that's kind of an easy one. I want you guys to compare and contrast this question to the next one.
Thank you.
Yep. So pretty simple, right? You got a particle moving along a curve. And then this is kind of a variation of that same question. Or a similar, it's a particle still moving along a curve. Another example. Particle moves along the curve again. Oh, wonderful. This time it's a nice square root curve. And then as it passes through the point 4, 2, the x coordinate increases at a rate of, again, 3 centimeters per second? Okay. Now here's the question here. It's a different question here. How fast is the distance from the particle to the origin changing? Okay, you guys have you guys written this stuff down yet? This is an interesting variation of the last question. Okay. Let me see if I can do this for you guys. Here's a curve. Y equals the square root of x. Let's say here's 4, and here's what? 2. It is not to scale. I think, is it 4, 2? Yes, it says 4, 2. Okay. So your particle is moving along that curve. You guys good with that? Now, what did they tell you here? This is the x coordinate and the y coordinate here. What did they give us? The x coordinate, I'll color it green. The x coordinate increases, okay, at a rate of 3 centimeters per second again. So that's the x coordinate increasing. That's a rate. So dx dt equals positive 3 centimeters per second. It's increasing again. Okay. So far, so good? And then they're saying, how fast is the distance from the particle to the origin changing? So you say, what? Here's a particle. Here's the origin. You okay, guys okay with that? And this is D. D for what? Distance. So as this particle is moving along this curve here, there's various distance values. Okay, you guys see my point? There's various distance values. Okay. So I'm going to do something here. I'm going to take an arbitrary point x and y. Turns out we need that, okay? And yes, here's D. So we're going to have to go back to some geometry and remember the distance formula. Okay? The distance formula from geometry. But this time, it's going to be the distance from what? This xy coordinate. I'm going to erase everything here so you guys don't get kind of confused here. Okay? We're looking at that D, that distance from the origin to some arbitrary point on the curve. We're going to have to write, you're going to use the distance formula. Do you guys remember what the distance formula was from geometry? All right. Square root x2 minus x1 squared plus what? y2 minus y1 squared. All right. Isn't that the distance formula from geometry? Do you guys remember that? Easy peasy, lemon squeezy. Okay, you guys with me on this? Now, I'm going to say this to you guys. This is my second point. This is my first point. So x1 and y1, these are both what? Zeros. Okay, you see that? What's x2 and y2? Well, x2 is just x, so this is an x. Is that right? y2, ladies and gentlemen, is the square root of x. You say, why is that the square root? Because we have here, this is the corresponding y value in general, square root of x, because they're saying y equals the square root of x. That's probably something you guys didn't know or notice here. So remember, this is the second point. And now we get a nice function here. We say, what do you mean? D is the square root of x minus 0 squared plus the square root of x minus 0 squared. And ladies and gentlemen, the square root, this is the square root of x squared plus x. Okay, you guys with me on this? Okay. Now, I'm going to do something here for you guys here, okay? I'm going to do something kind of interesting here. I'm going to say to you guys, if you square both sides, you're going to get d squared is x squared plus x here. Something going on next door. I think I want to go to the lecture. See, what's he talking about? That sounds interesting. Sounds important. Anyway, you guys okay with this? All right, now you might say, what's going on with these questions? Well, they gave us dx what? dt. They want to know how fast is the distance. Oh, what do they mean by this? Is the distance from the particle to the origin changing? Isn't that d? So they're asking for this question. What is dd dt? That variable. How fast is the what? Distance, that's the d. From the particle to the origin changing, that's this d right here. Isn't that the d? And then d dt of what? D squared is d dt of x squared plus d dt of x now. So I'm going to give you guys a few minutes to try to get this equation on your own. What do you guys think? Can you get that related rates equation? Give you guys a few minutes to try that on your own. Let's see if you guys can get that related rates equation. Finish this off. We're going to go over it, though. See what you guys get. Okay. All right, you guys. What did you guys get? You guys, what do you guys think? Okay. What do you guys notice over here? This and this. We're going to have to use what? Chain rule. Chain rule. 2D. dd dt. And then 2x dx dt. And this is just really, there's no chain rule here. This is just dx dt. Is that right? Okay, good. So if you guys are getting these kind of equations, good for you guys. And so I think here we'll say 2d dd dt will be 2x plus 1 times dx dt, right? Notice they're asking for this. We already know what dx dt is. I believe I painted it green, and it's 3, yes. There we go. We put it down here. Is that right? So that's going to be 3 here. Okay. So 2d dd dt is equal to 3 times 2x plus 1. Or I can just say dd dt, ladies and gentlemen, will be 3 times 2x plus 1 divided by 2d. Is that true? Okay, just doing a little bit of algebra. Is that right? Okay. So notice what's going on now. We need an x variable. Is that true? And what else do we need? D, and D represents distance. And you say, how do we get those two values? Well, what they're talking about is, now here, what they're saying, at this location here, D, here's the x and here's the y value. They're saying at that instant when it passes through 4, 2, so x is what number? 4. When it passes through that point, this is the value of x they're talking about. X is 4. It was orange. Okay, let me go back and do my colors here. But what don't we know? We don't know what D is. How do you guys think we get D then? Good. You plug in not just x. What do you guys plug in? The distance formula.
Yes.
You guys know what I'm saying? So this is like the second point now. This is still your first point. So x here will be 4 for x2. Y2 is 2. And then this is still 0 and 0 here. This is the x coordinate and the y coordinate for your distance formula. So what I'm saying to you guys, we're focusing now on that piece of information for it. And so it looks like my D is going to be what? If I do a little bit of some arithmetic here. Okay, I'm going to get rid of that because it's all in your notes or it's in the video already. So just so that you guys know then, it looks like D is going to be the square root of what? 4 minus 0 squared plus 2 minus 0 squared, which will be square root of 16 plus what? 4, which is square root of 20. X is 4 and Y is 2. So you can plug in X is 4 and it should give you the same thing, right? And so it should give you the same thing. You're going to end up with, really, if I simplify this, radical. Okay, we say, isn't that, square root of what? 4 times 5, which would be square root of 4 square root of 5. And so my distance is going to be 2 square root of 5. So now, 2 square root of 5. So d dt becomes 3 times, what's 2 times 4? Is that 8 plus 1? Isn't that 9? Is that 4 square root of 5? Okay, so double check my arithmetic, ladies and gentlemen. So it looks like d dt, that rate will be 27 over 4 square root of 5. And I guess that's red, so, okay. So there you guys go. Again, another classic related rates question. Anyway,
Professor, I have a question.
yeah.
For this type of question, is the formula provided?
No. In fact, the geometry distance formula, no. So you might want to remember that one. So they don't provide that formula for this one here. And I'm looking for some more questions that might be pretty good. Anyway. Okay, let me give you guys another example here. We could do a lot of these. I mean, I kind of like. The question is that. I've got tons of examples that I would love to do, but let me see. Question 8, maybe? Yeah, let's try something like this. What does question 8 say? Maybe it isn't question 8. What am I looking for here? Where's the kite question? Where is that kite question at? No. All right, maybe the kite. Yeah. Okay. How about this? You're going to look at the kite question, kite example. Try something like this. Here's a kite question. A kite is 100 feet above the ground. So we're going to say that. Moves horizontally. Okay. at a speed of, that's the same as a rate, 8 feet per second, okay? At what rate is the angle between the string and the horizontal? Decreasing. It's going to be negative when 200 feet of string has been let out. Okay, it's another classic question. Okay. Here we go. Kite. All right, so you might say a kite is 100 feet above the ground, moves horizontally at a speed of 8 feet per second. At what rate is the angle between the string and the horizontal? Okay, now here's what I want you guys to recall. Now, for me, ladies and gentlemen, here's kind of what I see personally. Kite is 100 feet above the ground. So this is 100 feet. Okay? And so the kite is moving how? What do they say the kite is doing? It moves horizontally. They didn't say, but it moves horizontally to the ground. You guys with me on that? So, in some ways, you can say this is where the kite is. And it's moving horizontally to the ground. And I'm going to do this here now. And that's kind of the idea. This is the ground here. Okay? And so the idea is that this here is going to be where the string is. Is that right? Now, I drew it this way because I want you guys to understand, we can think of this kind of as an x coordinate. And so they gave us dx dt, which equals what? 8 feet per second. Okay? And then you might say, what's the question here? They're saying at what rate, so that's going to be a derivative because it's a rate, is what? The angle between the string, there it is, and the horizontal. decreasing when 200 feet is left out. So 200 feet of string is left out. So I'm going to put this here, just so people know eventually, 200 feet. And where's the angle? Where is the horizontal? Do you guys know what they're talking about of a horizontal? The horizontal, ladies and gentlemen, is actually here. It's that path. This is that horizontal. So they're saying really that this is the angle what? Theta. The angle between the string and this what? This horizontal. All right. Okay, now notice when they say that this is 100 feet above the ground, that this value here, this value is constant. Is that true? So what definition can I use here that's going to relate everything together? Anybody know? What's tangent theta? Because don't I have these values known here? I got theta, and I have 100, and I have x. Is that right? So what do we know about that? Go back to trig. You go, oh my God, Mr. Judge. Trig, it's kind of geometry. So I think tangent, what's tangent theta? It's opposite 100 over adjacent. Is that true? Which means cotangent theta is x over 100, or my x is going to be 100 cotangent theta. Okay, this is kind of geometry. Kind of trig, though, because you have moving kites. Anybody take a good trig course? You guys know what I mean? All right. So, all right, I got my geometry. I got my triangle. Now, what do I do with this? We need the related rates equation. Is that right? So, dx dt will be d dt of 100 cotangent theta. Okay. What's the derivative of cotangent? Is that minus cosecant squared theta? I don't know. I think so. Is that right? Times d theta what? dt. Isn't this going to be a chain rule situation? Okay. Is that chain rule, ladies and gentlemen? So we get dx dt will be minus 100 cosecant squared theta times d theta dt. This is the variable that they're looking for. Is that the variable? Let's read it. At what the angle of the string and the horizontal decreasing. At what speed? At what rate is the angle? Yes, the rate and the angle. So they're finding d theta dt. And I think dx dt, what was dx dt? Isn't that 8?
Yes.
So they told us this. This portion is 8. So now 8 will be negative 100 cosecant squared theta d theta dt. So then, if you wanted, d theta dt will be negative 8 over 100 cosecant squared theta dt. And that means, if you said, what does that mean? That's like negative 8 over 100 now. Really secant squared theta, the reciprocal, right? Okay, you guys okay with that? But then you might say, how do I get secant theta? So I'm going to say, what is secant theta? Yeah. Do I have that correct? Cosecant and secant? Or I think that might be wrong. Is that wrong? What is this? What's a reciprocal of cosecant? That's not true. What's a reciprocal of cosecant? Is that sine squared? That might be better. Okay. And then I think I can simplify whatever that is. Isn't that 4 over 50? Is that 2? So let me simplify this. D theta dt will be negative what? 2 over 25 sine squared theta. Now, the question is, what is sine? Do you guys know the definition of sine? Opposite over what? Opposite over hypotenuse. Is that true? So opposite 100 and what? What's the hypotenuse? 200, which is 1/2. So this would be 1/2 squared, I guess. So if we say, okay, what is this? 1/2 squared, right? Which is 1/4, I think. Okay. So d theta dt will be 1/4. So it's negative 2, 25 times 4. Negative 1 over 50. And that's going to be in radians, ladies and gentlemen. Okay? That's a radian measure, by the way. And then notice it's negative, so it's decreasing. So this is in radians per what? Whatever that time was. It's a decreasing rate. So that angle is actually what? Decreasing. Radians per, what did they say? Rate is radians per second. What's our time like? So anyway, I don't know. Boy, there's so many different kinds of questions. Should we open the door to a law of cosines? Should we really give those people with trig a fit? Law of cosines? Ooh, I got a bunch of questions. I love them. What's our time like? Boy, I love this question here. I love a lot of these. Darn it. Whatever. Anyway, what's our time like? Look at all these. I have all these notes. Do I have anything on my website? What's on the website? Anything to see? Let me go back. I don't even remember how to use all this. This is trig. Oh, there's a trig class for you guys. This would be two what? 261. Let's see if I have anything interesting there. Do I? Did you do it? Let me see. Can't even remember. I'm not even awake. I even have a video. Oh my God, related rates. What did I do? Should have went with my worksheet. I don't even remember. I got so many resources there. I'm just going to put them all out and for free. The publishers don't make you buy. Oh my God. Hey, you are right. I do have a bunch of things there. Darn, I'm going to say to you guys, hey, look over these notes. Good. You guys have a lot of information. Oh my God. I should have just done that. I forget. Okay. Oh my God. Look at that, ladies and gentlemen. So you got these examples I did here. Oh, that looks like we did this one here, right? Oh, do we do that one? Ooh, we didn't do that one. Example 6 is a good one. Oh, example 6 and 7. Oh my God. Oh, I did the kite one for 8. 9. Oh, there's a law of cosines question. Woo. So 10, what is that? Oh, the ladder. That's kind of like a trig question. Oh my God, there we go. And then what did I do? I went crazy. Oh, I really went crazy. Boy, there's another one I did. That's what's on all my notes too. It's not a vector. They're not vectors. It's actually law of cosines. But it goes back to those trig students with navigation and those things. See, I do that in a trig course. And their applications of law of sines and law of cosines. I do it. I don't know about other instructors. I hear not everybody does. But I do, because it's like, why would you learn trig if you're not going to apply it? See, I'm an applied mathematician, not a pure mathematician. And what motivated me personally were all the applications. So, oh my God, these are some all beautiful examples. I completely forgot what I did. Should have just said, here, do this. What is the rate of increasing distance between the cars 3 hours have passed? I put a lot of time and energy into this, by the way. That's navigation, A and B and the angle between them, and then D, that's a classic law of cosines. That's side, angle, side information. And then you're right, it looks like I did what? What did I do? There is a video. So maybe for Halloween, instead of watching a scary story, you guys maybe want to watch this. Oh, what the? That doesn't. Wait a minute. What's going on here? That's not right. Is that my Adobe Muse thing? You click, because Adobe Muse is a weird. I do this in Adobe Muse. Anyway, where's related rates? The video. I got to be careful what I hit. I got to now I got to go back home and, it's not there. Did you see the video, by the way?
Yeah.
I wonder why I can't get to the video. Is it at the bottom? All right, I'll have to get the video and make sure that one's there. I don't know. What it is Adobe Muse doesn't always put the link. I'll do that. I did do this, and then I'll send you guys the what. If you want to see some of these questions, some of these examples, if you like, have some fun. You already seen some of them. If you want to watch some of these as well, the motion with cars, that's interesting. Distance is rate times time. But anyway, I'll make sure that video is functional when I get home. Always doing something. But, I did put some kind of questions for you guys. I might modify it, okay? I might modify it in homework 3. I'll have to take a closer look. I'll do that in my office hours. I put what is that? 17 odd. I might modify some of that. Anyway, look over that video too if you guys like, and take care, stay safe, have a wonderful day. We'll see you guys tomorrow. Welcome back on a Monday. No energy Monday.